Okay, so thanks a lot, Mirko, for inviting me. So I'm a bit in a tough situation because Anna's talk was so good. I would have preferred a less good talk so that I can shine now, but instead here I'm just going to lower the level, really. So what I'm going to talk about today is a project that started around 3 years ago with Vincenzo Gioia, who was a visiting PhD student from the University of Trieste, his supervisor, Ruggero Bellio, and he kind of was motivated by previous work that I've done with Jethro from the University of Glasgow. He's a specialist in kind of electricity kind of applications, and then he also my former, long-time collaborator and former PhD supervisor, someone who was involved, especially in the methodology. So in terms, it's nice that this talk is kind of coherent with the one that Anna gave. It's on a similar kind of topic in terms of application. So we start this talk by giving some motivation, and we talk about the application where we are modeling the joint net demand across the UK grid. That's the first part. Then I will briefly explain the kind of the models that we want to use to do that. Then I will show the results that we obtain by applying those models to the data. And finally, we will look at some computational challenges that we encounter. The plan, I plan to go through 1 to 3. If you have questions, you can stop me. I don't mind. Actually, maybe better even if you have already gone through one talk. So maybe it's better to keep it a little bit more interactive. You know, if we get up to here, it's also enough if we manage to cover the computational part. It's a bonus, but it's more kind of a more specialist topic. So yeah, maybe the first 3 points are more interesting. People are not specialists in kind of my kind of area. So this is a picture of Great Britain, the island. If you take a transmission network, so the high voltage network that takes electricity through the UK, that can be divided into a few hundreds of what are called the grid supply points. These are connection points between the transmission network and the distribution network, or a big industrial customer, let's say, like a steel manufacturer. Okay, so these grid supply points, they can be bundled together into what are called the grid supply point groups, the GSB groups, which are those that you see here. We have 14 groups. This is London. This is kind of a small region. So what we did in a previous work with Jethro was to model and forecast the net demand for electricity across these 14 regions. Net demand is the demand for electricity minus, so net of the embedded production from, for example, solar panels. Okay, so modeling demand minus renewable generation that is embedded onto the grid. So in the previous work, we did it separately, so with 14 models. And what we did more recently was to, skip 2 slides, was to model it jointly, okay? So we want to model the joint distribution of net demand across these 14 regions, okay? So one reason to do that, one kind of possible then application for such a forecast, is to then forecast or model the power flows of electricity across the regions. So essentially the data that Anna was talking about. So the reason why we need the joint forecast is that, for example, if you take, so here we bundle together the region in groups, such as we have the north, so Scotland, where we have a lot of wind, the north, the Midlands, and the south, where we have more solar. Then London is always kind of a special case on its own. If we want to model, for example, imagine the electricity flowing through this border, the Scottish-English border, we don't need to know just, if we want to have a probabilistic forecast, we don't just need forecast for Scotland of demand. And for the north, we need to have the joint distribution to know, because the flow is going to depend on the value of net demand across the border. So we want a joint forecast across the 14 regions, and we also want to be able to kind of post-process that forecast to aggregate regions in ways that are kind of meaningful for example, the national grid, the company that manages the transmission grid. Okay. Now the key challenge that we focused on when doing this is the fact that the dependencies or the correlation across the regions, they're not constant, but depend on many factors such as weather, the time of day, the day of the year, and so on. Okay, so here, just to show you that the correlation and covariance of demand is not constant, I'm showing you, kind of giving you already an idea of what will be the output of the model. So here we have a graphical representation of a covariance matrix of net demand across the 14 regions. So the nodes here are the regions. So north of Scotland, south of Scotland, Yorkshire, London is 11, Cornwall is there. So the nodes are the region. The colors of the nodes are brighter if we expect that there will be more variance of net demand in that region at that time. Okay. And the edges are just, so here we have all possible nodes are connected, but the brightness of the edges is proportional to how strong is the correlation between the net demand across those two regions. Okay. So we have very different situation here. We have a very hard day to forecast, very hard moment actually, because we're looking at 7 a.m. on New Year's Eve, 2018. So what you see here is that the model forecast predicts that there will be big errors we're going to make in many regions, especially highly populated regions such as the West Midlands. And also that those errors will be highly correlated across the regions. So essentially, this is telling you that on New Year's Eve, you're going to do big mistake, and the sign of the mistakes, the forecasting errors you're going to make, they're going to be the same across the regions, which means it's particularly bad. Yeah. So essentially, yeah, so this, of course, is a model output, because at 7 a.m. on these days, you have a vector of 14 observation, which by itself doesn't give you a correlation matrix. You need to have a model that tells you what the correlation is expected to be. And then here we have a much easier period where to make forecast. So here it's like a mid of August 2018 at midnight. So the summer is already kind of an easy, calm period, and the night is also a calm period. So middle of the night in the summer, it's going to be kind of very easy to forecast demand. So you see the nodes are kind of very dark. So essentially, you're going to do small forecasting errors in each region, and the errors are going to be weakly correlated across the regions. Okay. So this is model output at the regional scale. Then, as I said before, we might want to say we want to actually focus on these kind of macro regions because some borders, for example, are particularly interesting for the forecasting then the flows potentially. So if we focus on these 5 micro regions, we can take this sort of forecast and look at this kind of the covariance matrix represented by this network. So here we're looking, so the regions are the Scotland, the North, Midlands, London, and the South. And here we're looking at the central plot is what the model predicts for 10 a.m. on the 16th of June 2018, which was during a storm Hector. So it was a storm in the UK, so were really high wind speeds. And then what we try to do, just to demonstrate what you can do with the model, is to say, well, let's do some kind of sensitivity analysis of some scenarios. What happens if the storm intensifies, and what happens if we increase wind speed and precipitation by 25%? That's what the model will predict, which sort of makes sense. We predict very bigger errors in the north, here where we have a lot of wind turbines installed. Okay, so just to show that actually this seems to kind of make sense what the model outputs. Okay, so these are the results that I haven't told you what the model is, which is then coming in the next part. So just to kind of set up things a bit. So the response variable, what we want to predict, is the net demand across these 14 regions at half hourly resolution. So we have 48 observations per day. Kind of, I would say, one of the simplest models we can think of for kind of multivariate probabilistic forecasting is the multivariate normal, where both the mean and the covariance matrix will change with I, with the observation index. Now, to model the mean, that's fairly standard thing to do. What we can use is to use an additive model. So the mean is going to be modeled directly by the what we call in regression modeling the linear predictor. So the thing we actually modeling as x beta. And we're going to use a additive model that is the sum of some effects of some covariates that we call x. Okay, so the mean is sort of standard thing to model in the sense that we can model it directly without any constraint, okay, via what either linear or smooth effects. So in terms of the smooth effects, so the FJs we show here. So if you want to have if you know that the variable has a nonlinear effect, we are going to use smoothing splines. So these are to build a spline. We have a linear combination of some basis function, the b's here, which are known and fixed, times some regression coefficients, which are unknown and need to be estimated. Okay, and then to avoid overfitting, we usually have a prior on the betas, and the prior is trying to push the effect towards smoothness, so for example, toward a linear fit, and the strength of the penalty of the prior is proportional to lambda. So the stronger, the higher the value of lambda, the more we are going to shrink the fitted effect toward a straight line, for example. Okay, so the mean is sort of standard thing that we can model without worrying too much about constraints. The problem is how to model the covariance matrix. So of course, if we take the covariance matrix and we try to model it element by element directly, the sum of some effects, that would not work because we will easily break the positive definiteness of the covariance matrix. Okay, we will easily, especially if the dimension is fairly high, we will surely violate the constraint that this matrix needs to be positive definite to be a covariance matrix. So that's not going to work. So what we did, the approach we follow is to instead use an unconstrained parametrization of sigma. So we reparameterize sigma in such a way that we can work without any constraint while knowing that the covariance matrix in the end will be positive definite. There are a bunch of parametrization that are reviewed, for example, in this paper, or more recently in this one. The particular one that we used is called the modified Cholesky decomposition. So this works like this. So you take the inverse covariance of the precision matrix, and you decompose it into a diagonal factor and a triangular factor. In terms of constraint, the only constraint is that the diagonal elements of this matrix, they need to be positive. So we are going to work on their log, right, and exponentiate it afterward. So the etas here are the things that we're going to model directly. Those are the unconstrained parameters, the linear predictor. Okay, we're going to model it, the log, the diagonal elements of this. The triangular factor is completely unconstrained. It needs to have unit diagonal, but all the sub-triangular elements, they are all unconstrained. So all these elements can be modeled directly as sum of smooth effects or linear effects. So if you use this parameter, just keep in mind that in terms of parameters that need to be modeled, we have 14 means, one for each region. And if you count, the total for, in our case, we have 105 elements between the T factor, the triangular factor, and the diagonal. So that's a lot of models in a regression context to specify. We have 119 models that need to be chosen to model all the mean vector and all the covariance matrix. Okay, so this point, if you have questions, let me know, because it's very important to get this. This is the most important slide, maybe. So why this modified Cholesky decomposition? We chose it mostly because it has a useful interpretation that is key then for what comes next. Okay, without this interpretation, things will be quite hard. So imagine we are modeling y is the vector of our net demands. Let's say that the first one is north of Scotland, and then we're going south from there. Okay, so that's our y. Let's say we want to compute the residuals r, so y minus the mean. Okay, Now the covariance matrix of the residual is going to be sigma, which we can decompose using this modified Cholesky decomposition, okay? So it turns out that the elements of this modified Cholesky decomposition have an interesting interpretation. So I don't know whether this is the best way to explain it, but let's try. So imagine we take the first residual, we try to simulate some residuals, okay? The first one, R1, which is going to be the residual for the north of Scotland. We simulate it with mean 0. It doesn't really matter the distribution. The important is that it needs to have mean 0 and variance, which is given by the first element of the diagonal factor, okay? So having simulated this, we simulate all the following regions and going north to south from this sort of autoregressive process. So essentially, for example, if we take if we want to simulate the residual for the south of Scotland, we are going to multiply the residual from the north of Scotland by this element, which is the first here, some diagonal element there, plus some error. And this error will have variance, which is the second diagonal element. So essentially, what this interpretation of these elements here, they are sort of autoregressive coefficients of the residuals of each region on the preceding regions. For example, in the third row is Yorkshire. The residual from Yorkshire can be simulated by essentially regressing on the residual for the north of Scotland, the south of Scotland, plus an error whose variance is the third diagonal element, okay? So the reason why this, and then if you follow this, essentially if you follow this process, the covariance of these residuals is exactly sigma, okay? This gives you kind of generative process that has some interpretation and leads to a covariance that is the one you're actually modeling, okay? So why is this useful? Because suppose you have to decide, yeah, as I said, we have 105 models to specify. You have to decide what we want to model. Suppose you have the idea that wind speed should be really important to model the correlation of the dependency between the north and the south of Scotland. Then that's the element you should be targeting, because that's a kind of regression coefficient of the south of Scotland on the north. Okay, so that kind of captures the dependency between the north and the south. Conversely, if you look down here, this is going to be Cornwall, the last region. This is sort of the dependency between Cornwall and the north of Scotland. So those regions are very far. So you would think, well, that's not really something that I think is important to model as a function of covariance. Okay, so this gives you some kind of reference point to kind of understand what might be useful to model and what might not be. Okay, so this is very important for model selection, and it has also computational advantages using this parametrization. Okay, do you have any question about this? We see this kind of again, because it's important. So this is essentially the model. So multivariate normal, the mean is sort of standard in an additive modeling context. The real challenge is modeling the covariance matrix, and we're using the MCD because of its interpretation. So now we apply this model to the data on net demand. So again, total we have now 14 mean models to specify and 105 models or linear predictor for the covariance matrix. So for the model, luckily because we are building on previous work, we can adapt a formula a model that we have used before in a previous paper. So Jetro did a lot of work to come up with this formula. So we are applying this formula with a bunch of effects to each of the 14 regions with some modification, because with time we found that we could improve a few things. But just to give you an idea, so these are all effects. The G's mean a linear effect and the F's means smooth effects with a penalty. So we have a time trend, then various kind of what we call calendar things, so having to do with the day of the week, holidays. Down here we have the day of the year, the time of day. Then we have a bunch of weather variables, temperature, rainfall, wind speed. And then all these bivariate effects from this point onward, they are all interactions because we are modeling the demand across the day.
And we know that the effect of temperature is different depending on the time of day you're targeting. So we need everything to interact with the time of day. Okay, so this is fairly complex formula, but it sort of could exploit some previous work. The challenge was instead how to model the remaining 105 elements of the covariance matrix. So what we did was to say, okay, let's say that potentially it is, so these eta ij are the elements of the modified Cholesky decomposition. Potentially we could use a model like this, kind of an over-specified model. So imagine this 105 times for each of them. And this is kind of our candidate pool. Okay, this defines the pool of candidates we're going to choose from. So the candidate pool means that in principle we could model each element of the MCD via a time trend, day of the week, day of the year, so seasonality factor, time of day. This is wind speed multiplied by the installed capacity of wind turbines. This is solar irradiation, temperature, rainfall, and this is electricity price on the N2EX price. Okay, so that's the kind of over-specified model. The kind of defines the pool of candidates we're going to choose from. Just one, then already here, the kind of the MCD becomes useful. As I said, this is the definition of the modified Cholesky decomposition. Now we have a model selection process that we want to, problem that we want to solve. Suppose that we're looking at a linear predictor that controls some elements of T, right? Now, if suppose that we didn't have any interpretation for our decomposition, we just know that there is an element that needs to be modeled, okay, with a formula such as this. So here, for example, I say, okay, let's use temperature. But the problem is that we don't have one temperature, we have 14 temperature. We're using a weather forecast that gives you a forecasted temperature for the north of Scotland, for London, and so on. When I'm looking to model an element of the MCD, I need to plug in a temperature there, and I have a choice of 14. So that's a big model selection process and problem. And the way to solve it is again exploiting the interpretation of the MCD. As I said before, for example, this element is the regression coefficient of the south of Scotland on the north. So it makes sense that if you want to model this one as a function of temperature, it should be the temperature either in the north or in the south of Scotland or both, but at least you have some idea. Okay, so what we decide to do, which might not be optimal, is to go sort of row-wise. So this row is related to the north of, to the south of Scotland. So here we're using temperature in the south of Scotland. This row is related to Yorkshire, regressed on the previous region. So we're going to use temperature in Yorkshire. Okay, so at least we have some reference point, otherwise it would be completely impossible to come up, to find what's the covariate you should use for every element. Okay, but the MCD already kind of made our life easier here. So at least looking back at this formula, we know what temperature to plug in. We still have the problem of having 105 of these formulas, and we need to choose whether we want to have all these effects or only some. So as I said, we have 105 parameters that need to be modeled, and if you count back, we have some 9 effects for each that we could choose. Okay, so we still have 1,000 possible effects that could be added somewhere in our model. So what we did is kind of a greedy approach, which again could be improved, but worked reasonably well. Essentially, we use gradient boosting to do variable effect selection. So gradient boosting here, I just give you kind of basic recipe of what we did. We took some training set, I think it's the first 3 years of the data we had. And until we see that we start overfitting, we do the following. We take all the linear predictors, all the parameters of the model, and all the possible covariates that we could use, and we regress the gradient of the log likelihood with respect to the linear predictor on the covariate to get an estimated effect. We find so we do this for all the possible combinations. Then we find the effect that is the best, the one that improves our fit the most. And then we add to the corresponding linear predictor a fraction of that effect. That is called the learning rate. So the value of 0.1 is kind of the standard value that people use. So this is essentially just the basic gradient boosting. Then what we do that is different is that we store, as we go along, we store how much we gain by doing each update to our model. And in the end, we get the ordered list of effects that is kind of decreasing in terms of how much did you gain by adding each effect. So we can imagine that we have a list that says adding the effect of let's say wind speed on the parameters controlling, the correlation between the north and the south of Scotland was the best thing you could do. And then it goes down from there. We still have hundreds and hundreds of effects. And the question then is just where to cut. So we choose the number of effects to include in our final model using a validation set. Okay, so we use this kind of greedy procedure without any constraint or not much knowledge built into it. We just find pool of candidate effects, order that, and just then we decide where to cut using a validation set. So this takes a few hours on a workstation. So the good thing is that the results in the end they kind of make sense, even though, as I said, this procedure is quite naive, doesn't use any knowledge really. So here you have a representation of the modified Cholesky decomposition. You have the diagonal here. The region are going north to south or north of Scotland. 11 is London, and this is Cornwall. And the symbols here, they are the effects that have been chosen by gradient boosting. And the color here is how much did we gain by adding that effect in that location of the particular element of the modified Cholesky decomposition. So the empty elements here means that these elements, they are considered constant. They're not zero, but they are just not being modeled as function of the covariance. So the output sort of mostly matches what we thought should be, we should do, essentially. So you see, if you look at this square with a cross in between, that's the time of day effect, and it appears everywhere along the main diagonal. That's quite intuitive. That's saying that essentially the variance of demand depends on the time of day. So it's different between day and night, and that's true everywhere. And it's particularly true. So this symbol is particularly bright in the south, which makes sense because we have a lot of sun, of solar generation, which is highly correlated with the daytime. And also it's important in London, where we have a lot of peak and off-peak kind of dynamics of commuting. Another thing that is intuitive, if you look at this upward triangle here, it appears down here in the south and southwest. That's the effect of solar irradiation. Again, it makes sense that that effect is very important and is chosen to model the variance in the south of England, where most of the solar panels are installed. And similarly, if you look in the north, if you look at this star-shaped symbol, it appears in both the north and the south of Scotland. It's very bright there. And that's the effect of wind speed. Of course, wind speed will have a big effect where you have a lot of wind turbines installed. Okay. So it's easy to interpret the diagonal elements. Off the diagonal is a bit hard. Maybe one element that is interesting is this one. So this is between London and the West Midlands. You can think of it as being the correlation between those two regions. This is the effect of time of day. So it's nice to see that it's there, because it means essentially you have these two highly populated regions that are kind of neighboring. It makes sense that they have kind of similar daily dynamics. And so it makes sense the correlation depends on the time of day. But of course, I wouldn't be able to interpret all the elements there. So this, up to this point, was just model selection. How do we, so what is the, so we saw before the actual model we want to fit, multivariate and Gaussian. The way we fit it is not by gradient boosting, but by essentially empirical Bayes methods. There are two things that need to be estimated, is the smoothness of the effects, which is determined by these lambda smoothing parameters. To do that, we use a maximum Laplace approximate marginal likelihood methods. And having for each value, so it's two nested optimization. Every time you kind of do a step in this optimization, you then get maximum posteriori estimates of the regression coefficients. Okay, so that's a kind of complicated nested optimization. So in terms of software, the optimization is implemented in the MTCV package in R, which we extended via the SCM package, where Vincenzo at that time was a PhD student. I put a lot of work into doing that very efficiently. So essentially, the optimization happens in MTCV, but you need a lot of derivatives and other kind of quantities that are computed in via this package. Okay. Now, before showing you kind of some extra results on this data, just keep in mind that what we are modeling directly is the element of the MCD, which maybe is not if you need to present to kind of general audience. It's not they are interpretable only up to a certain point. What is more interpretable is directly looking at variances and correlations across the regions. But so what we're going to show you next is the effect of the variables, the covariates, on variances and correlation. And we do that via looking at accumulated local effects, which are needed here because there is a nonlinear relation between what you model, the elements of the MCD, and what you want to visualize, which is the variances and correlation across the regions. Okay, so let's look at some results. Let's start like here. Here you have the time of day, and on the y-axis you have the standard deviation of demand in some region. So you can think of it as being standard deviation of the forecasting error that you are predicted to make. So here what we have, you have in red you have London. So in London you see that you do smaller mistakes at night, and then you clearly see kind of the peak, the morning and the evening peaks time, where you're expected to do bigger errors on average. In the south of England, which is this green one, things are probably more driven by kind of solar. So you do more mistakes during daytime, where there might be some solar production, and fewer mistakes at night. In the south of Scotland, where you have less sun and a slightly less densely populated area, you have some effect of the time of day, but it's not that important. If we look up here, so here we look at correlation between some pairs of regions that I have chosen, and not so as a function again of the time of day. So just to pick one that is kind of interpretable, maybe this one, the correlation between London and West Midlands is the green one. So here you see that these are two densely populated areas that are also neighboring. And you see here that you're expecting to have a lot of correlation under the morning peak hours, and again in the evening, and less kind of in the middle of the day. Okay. Then if you look down here, again, you look at standard deviation of the errors as a function of the day of the year. So all regions, we have some bumps in the spring that might be related to, for example, to Easter, which is a very hard period to forecast. But there is some, not all regions behave the same way. Roughly speaking, you have the easiest time of the year to forecast is kind of the summer. And then in all regions, you see a spike just before Christmas, because before Christmas, many businesses are closing, there are many things going on, and it's very hard to make a good forecast, particularly in densely populated regions. So in London, the Christmas kind of spike in forecasting error is really big. So the errors here are expected to be double in size than they are in the middle of the summer in London. Okay, so you know that before Christmas you're going to do big mistakes, and this plot, which is again day of the year and correlation here, shows you that if you look at some pairs of regions, also the correlation between the errors are going up. Okay, so during just before Christmas, you'll do big mistakes, and we'll do the same. The mistakes will have the same sign across the regions. So it's a particularly hard period to forecast. So these are kind of time variables. Keep the slide. So this is the effect of weather variables. So here you have forecasted wind speed, its effect on the standard deviation of the errors across some regions. You have north of Scotland, south of England. You see the effect is quite big, especially in the north of Scotland, where most of the wind generation is. So in terms of how to interpret this strange shape, this interpretation comes from Zetro, who is kind of expert on this. If you have zero wind or no wind, there is no uncertainty related to wind production. As you start having more wind, there is more uncertainty because the turbines might be working, might be producing, but not kind of a full speed. You know, there's some uncertainty about the rate at which they might be producing. Then you get to a point where the uncertainty decreases, and that's because the turbines start working at the steady state. So they have a reliable kind of rate of production. And then it goes up again because you start having kind of storm level winds. And at that point, if the wind is too strong, you might have to turn off like a wind turbine to avoid that it breaks. Okay. And similar, if you look at the plot down here, so here we have forecasted solar irradiation times capacity, the installed capacity of solar panels across the regions. These plots here, they have different x-axis scales because the capacity installed is different across the region, but the shape is kind of similar. And the explanation for this shape is kind of similar to the one before. At night, or when you have a completely overcast and clouded conditions, there is no uncertainty of related to solar production. As you get more sun, you might have like intermittent clouds, and the production is uncertain, so you have more uncertainty. When you then at some point you have clear sky conditions where you are certain that you're going to produce a full capacity, and then the variance goes back down. Okay, so I think most of the plots, they can be interpreted. Of course, it's much easier to interpret the plots on the marginal kind of variances than the correlation across regions. Okay. Have you got any questions on this? All right. Okay, these are kind of plots to show that we can kind of interpret the output of the model. We do also some model comparison to see whether we really need such a complex model. So the model for the pool of candidates to model the covariance matrix was given by this old formula there, which we call the full model. We're going to pick using gradient boosting some effects there, but that's the full candidate pool. We tried a simpler model by saying, okay, maybe we just need a calendar variable, so the day of the week, time of day, day of the year. We call that the calendar model. Maybe we need that plus the renewable variable, so the variable related to renewable production, such as wind speed and irradiation, or we might need a full model. And we just tested each to see what's best. Essentially, in this table, I'm showing difference of the three models I just mentioned, and their performance in terms of some scoring rules, performance metrics. So this is the log likelihood out of sample, full log likelihood of the multivariate normal. This log likelihood, if you focus only on the margins and you assume independence across the regions. Okay, so this is a measure of how well you're forecasting each region separately. CRPS is a standard measure for probabilistic forecast, again focusing on the region separately and marginally. Pinball loss is again a marginal measure of how you're forecasting very low quantile at 0.001 level, or very high quantile of demand at 0.999 level. And this is the variogram score, which instead is a measure of multivariate goodness of fit. So it's trying to focus only on how well you are modeling the covariance matrix. So essentially from this table, what we see is that the calendar model is much worse than the next two. So it's really important to have this part make sense. So it's important to take into account variables that are related to renewable generation, because we are modeling net demand. And then the next step, if you include also temperature, rainfall, and electricity price, you might get some marginal improvement, but it's not so important. So you should go either for this model or that model. Then a further comparison that we did was to say, okay, this is a multivariate Gaussian. Of course, we know that it's unlikely that the data actually follows a multivariate Gaussian model. In particular, on the margins on each region, maybe we need fatter tails than the Gaussian. So we've used a fairly complicated kind of benchmark where we are modeling each region separately using this SHASH distribution, it's the sine arc sine distribution. Essentially, it has parameters for the mean, the variance, the skewness, and the tails, the kurtosis. We model the bulk of the distribution with that. It's quite flexible. Then what we do, we cut off the lowest 5% and the highest 95% percentiles. And we model those two tails separately with the generalized Pareto distribution to get the kind of the best possible tail models. So that gives us pretty good marginal models. And then on top of that, to take into account the correlation, we use the Gaussian copula, static, not something that changes with covariates, to take into account the correlation. So if you do that, if you look at these kind of marginal performance metrics, you do a little bit better than the multivariate Gaussian model. So here and on the extremely high quantile, which makes sense because now you have this Pareto distribution, which is quite good. But you do worse, for example, on all the multivariate scores like this one and the last one. Okay. So overall, I would say that the model, the multivariate Gaussian, does even better than I thought. You know, in comparison to a model like this on the margins, but it's still able to model also the joint behavior. And also, I think overall, you know, this one model, where this is a sort of Frankenstein sort of composition of three different models put together, right? Not very elegant, but yeah. Okay, so this is just one part of the comparison. Then in the paper there is more options we compare to. So to conclude on the kind of application part, on the modeling part, I would say the model provides a reasonably good forecasting performance, and it's interpretable. The model selection is the biggest issue. So if you have the response variable, which in our case is 14, you will have order d square linear predictors, so models, additive models that you need to specify. In our case, we also have ordered, we have d actually, weather covariates, so temperatures for each region, rainfall for each region. And here the MCD helps us a lot to understand which weather forecast should be used for which elements. And yeah, so but still, you know, despite this, we still have, you know, model selection is a big issue. We use this gradient boosting procedure, which is maybe not very elegant, or maybe we want to improve. Maybe one direction would be to say, well, let's model several elements jointly of the MCD, which will be particularly useful when, instead of dealing with response variables that come from different regions, if we are dealing with time ordered response variables, maybe there is more structure there. We could model several elements of the decomposition kind of together rather than element by element like we did here. Okay, so maybe just I tell you a few things without, okay, I hate when people skip through the slides very fast, but I'm going to do it. Just to tell this kind of insider stuff, because I think the part before was kind of maybe interesting to everyone. This part is really for kind of specialists maybe. But just to give you an idea what is the computation behind this sort of method and what are the challenges. So the biggest challenge is that when you're dealing with a response variable, oh, sorry, no, I'm going back here. Just so remember, this is the model, multivariate Gaussian. The key challenge is that if you're dealing with the response variable, so 14 regions in our case, the number of parameters you need to model is the square of that. So it's order d squared. Essentially, you have the mean, and then all the kind of elements of the MCD. That's not kind of standard in an additive modeling case. Usually, if you had, you know, in the old times, you had maybe univariate Gaussian with one parameter. Then the so-called gaumless models came, and then you're modeling the mean, the variance, the skewness, but still is a handful of parameters. While here, as soon as you have 10 variables, you have 100 parameters to model. So that was kind of the difference relative to what I've seen before. In terms of fitting, as I said, this is the formula. So there are two things that need to be estimated. The betas, the regression coefficient, and the hyperparameters. The betas usually is kind of the easier part. We do it by maximizing the Bayesian log posterior density, which is this. So usually it's quite straightforward. But here, if we want to do it by Newton method, we need the Hessian of this thing. And that turns out to be really big in this context. So the Hessian of the log posterior is the dominant cost. The reason is that, again, the number of parameters that we have is order b squared. And if you're looking at the Hessian, you need to square again because you have matrix itself. So you have order b to the fourth blocks in the Hessian. The Hessian is really big, and it's needed for optimization purposes. And that's just so order the square in number of parameters. Then you have to take into account the fact that you also have regression coefficients that you need to estimate. Let's say you have p of them for each parameter. The Hessian now is ordered, it has these b to the fourth blocks, each of them is p squared. And that's the Hessian for one observation. You have lowercase n of them. So you have like computing is quite involved. If you take kind of as a reference, the dimension we have in our problem, 14 dimension. Let's say p parameters for each p regression coefficients for each parameter. You have a Hessian with 300,000 elements. You have maybe 100,000 observations. You get to compute it will take 30 gigaflops, which means a few minutes. So just to get the Hessian, but the Hessian is just, if you know Newton method, the Hessian is needed multiple times, hundreds of times before you converge. You have to wait. Yeah, it's going to take days to fit this. What we found out, by spending time working out these derivatives, is that if you look at the Hessian, actually, there are some structures there. So that this is the kind of this basic structure of a Hessian block. There is this diagonal thing that is the derivative of the log right with respect to two parameters of it. And it turns out that these kind of diagonal elements, or diagonal matrices, they become more and more of them are actually equal to 0 as you increase the dimension. So your Hessian is getting really big, but it's also becoming increasingly sparse as you increase the dimension. And in particular, if you look at the elements, so this kind of key part of the Hessian, the ratio of non-zero blocks to total number of blocks goes down with 1/d. Okay, so essentially your Hessian is growing with the d to the fourth, because you have this sparsity is actually going with d to the third power. Okay, and if you look at higher derivatives, things are even more sparse. So if you look at third order derivatives, only 1/d cube of the blocks are non-zero. So you have this is the sparsity of the Hessian as the dimension increases, and this is the sparsity of the third order derivatives. Okay, so this sort of saved us. And then we said, well, we could have saved a lot of time and just do automatic differentiation. This is the case we're looking at. As a dimension, this is the time that automatic differentiation with the TMV package takes, in our case, as a function of dimension. And this is the time that we get if we take into account the sparsity. So you have in 50 dimension, you have almost 100 times speed up. I think the reason is that we take explicitly into account the sparsity when the automatic differentiation, as far as I know, cannot detect automatically, at least in our case. So it was worthwhile working out all these derivatives. As I said, this is about this part, how to get the regression coefficients. But the big problem usually is how to get the smoothing parameters that determine whether your fit should look like that or should be very wiggly. We do that by maximizing the Laplace approximate marginal likelihood. That, it has it's an approximation to this integral. Again, if you want to be efficient there, you need the gradient of your objective, this Laplace approximation. It has a very big formula, so I omitted a lot of terms, and I just say, okay, what is the thing we actually need? Is this big? This big? The challenging part. So what is this term here? Is it quantifies how your Hessian at convergence. So your doing optimization, you get beta hat. Then you have the Hessian of the log likelihood at convergence. Let's say that this is your beta hat. This is the Hessian. You want to know how that will change. So it's partial derivative of that with respect to a smoothing parameter. Okay. So if you look at the formula for this Hessian, it doesn't really depend directly on beta hat on lambda, but it depends on lambda indirectly. Because lambda determines beta hat, which is the point at which you evaluate the Hessian. It's quite complicated, and you need kind of implicit differentiation to get this sort of derivatives, and that in turn requires the third order derivative of the log likelihood. That's why I mentioned them before. So the third order derivatives without the sparsity is absolutely impossible to get them because you have order d to the 6 blocks. Sorry. But because you have order d to the third kind of level of sparsity, it turns out, which is kind of incredible, that because of this such a high sparsity in the third derivative, that the second and third derivative cost the same. So they have the same cost. Computing the Hessian cost you as much as computing the higher order derivatives, which means that with this outer optimization for the smoothing parameters, cost you as much as doing kind of the inner optimization. Okay, so that was kind of a miracle, which I didn't expect, but turned out to be the case. Okay, and then maybe we could think about what happens if we don't have that sparsity. There is something can be done, but let's keep that. Okay, so maybe let's keep these two. To conclude, so this was kind of computational part. As I told you, it's kind of insider stuff that a handful of people maybe are interested in, but maybe just to give you an idea of what we have done. So as I said, to get scaling, as you get more and more response variables, you need the sparsity of the derivatives, otherwise it becomes quite hard. Another challenge we encounter, if you look at the existing GAN method, the idea was to model the mean, the variance, the skewness, not to have 100 parameters, which is what we get. So there was a lot of work to do there, which was quite interesting. As I said, the model selection problem is still the biggest thing. Now we ordered our responses in a certain way, and then we have an interpretation, but still need to do a lot of work. In terms of current work, the idea is to try to model several elements of sigma kind of together, exploiting the interpretation of the MCD. That's what I'm working on with my student, Xin and a colleague, So, and if you're interested in the methods, there is this package which is fairly stable, still on GitHub, not on CRAN, which was a verify visit. Okay.
Okay.
All right.
Thank you very much.
Survived 2 hours.